Morning students, this is Arvind, Assistant Professor, Department of Triple DBS Kavali. So in the previous class I discussed about equivalent circuit of an single phase transformer, and next I discussed about the efficiency and magnificence conditions of a single phase transformer. And now in this class I am going to start the voltage regulation of a transformer and testing of a single phase transformers. Okay, so firstly I will start with the voltage regulation of a transformer. So before going to the voltage regulation, firstly we have to know about the regulation of a transformer, and after that we will go to the voltage regulation concept. So you know already, because of the voltage drop across the primary and secondary impedances, okay, it is observed that the second terminal voltage drop from its no load value, that is V2, to load value, that is V2, as load and load current increases. Okay, because of the voltage drop across the primary and secondary impedances, it is observed that the second terminal voltage drops from its no load value to load value when load and load current increases. So this decrease in the secondary terminal voltage, expressed as a fraction of the no load secondary terminal voltage, is called regulation of a transformer. Okay, so the decrease in the second terminal voltage. The decrease in the second terminal voltage expressed as a fraction of the no load secondary terminal voltage is called regulation of a transformer. So next, coming to the voltage regulation of a transformer. So the definition of this voltage regulation is: the voltage regulation of a transformer is defined as the change in secondary voltage from no load to full load with respect to full load voltage. So this is nothing but the voltage regulation of a transformer. Okay, so here we are considering two parameters, that is, let E2 is equal to, there is a second terminal voltage on no load, a secondary terminal voltage on no load, and secondly we are considering V2. So this is the secondary terminal voltage on given load. Okay, so next, so then mathematically voltage regulation at given load can be expressed as, that is, voltage regulation is equal to no load secondary voltage minus full load secondary voltage divided by full load secondary voltage. So that is equal to, no load secondary voltage is nothing but the V2 minus full load secondary voltage is nothing but the V2 by full load secondary voltage is V2. So totally we are writing this equation mathematically as E2 minus V2 by V2. So in the percentage we have to write the voltage regulation is equal to V2 minus V2 by V2 into 100. Okay. So next, coming to this one. So just now we calculate this one, V2 minus V2 by V2. This is called regulation, voltage regulation of transformer. So the ratio, that is V2 minus V2 by V2, is called per unit regulation. Okay. So next, the secondary terminal voltage does not depend only on the load current, that is the magnitude of the load current, but also on the nature of the power factor of the load. Okay, the secondary terminal voltage does not depend only on the magnitude of the load current, but also on the nature of the power factor of the load. So next, if V2 is determined for full load, okay, if V2 is determined for full load and specified power factor condition, the regulation is called full load regulation. Okay, if V2 is determined for full load and specified power factor condition, the regulation is called full load regulation. So as load current increases, the voltage drop tend to increase and V2 drops more and more. Okay, as load current increases, the voltage drop tend to increase and V2 drops more and more. Okay. So in case of lagging power factor, so that is for inductive load, V2 is less than E2. Okay, V2 is less than E2, that or E2 is greater than V2, and we get positive regulation for this case. And while for leading power factor, so this is for capacitive load. So that is when E2 is less than E2 is less than V2, and we get negative voltage regulation. Okay, so based on this, we have to draw the voltage regulation characteristics of transformer. Okay, by using this lagging load, leading power factor load, by using these things, we have to draw the characteristic diagram. This is the characteristic diagram of that one. Okay, So the voltage drop should be small as possible. Hence, less the regulation, better is the performance of a transformer. Okay, the voltage drop should be as small as possible. Hence, less the regulation, better is the performance of a transformer. Then the regulation characteristics for various power factors of the load is shown in the diagram. So this is the diagrammatic representation of the explanation. So here I am drawing a characteristic diagram between voltage and load current. So here I have drawn three curves. Okay, so one curve is indicating with the dotted lines, that is straight line. Okay, dotted line, it is represented with the dot line, it is in a straight line manner. So this is for ideal. That means in this condition, Vt is equal to E2. This is for the static resistive load. So actually we have three types of loads. One is resistive load, and another one is capacitive load, and another one is inductive load. So in the resistive load, the secondary voltage V2 is equal to no load voltage E2. So V2 is equal to E2. So at that time we have the straight line. So it is a constant. And next we draw two more curves. So one is for leading power factor. So in the leading power factor, we will get the negative value of the regulation. And for the lagging power factor, we will get the positive regulation. Okay, that means positive values. Okay. Next, so coming to the expression for voltage regulation from equivalent circuit of a transformer. So for that one we are considering the approximate equivalent circuit of transformer, that too it is referred to the secondary winding and its vector diagram as shown. So here this is the diagrammatic representation for the approximate equivalent circuit of transformer referred to secondary. So that means here we are considering the secondary winding, it is connected to the load. So you know already in the basic transformer we have two windings. One winding is connected to the supply voltage, that is called primary winding, and the other winding is connected to the load, that one is called a secondary winding. You know already these things. So here I am considering approximate equivalent circuit of transformer. So actually this approximate equivalent circuit of transformer refers to secondary. I discussed it in the previous class. Okay, so same thing I am taking here. So here I am taking approximate equivalent circuit of transformer referred to secondary. So that means we have resistor, inductor and load terminals, and we have parameters R02, X02, I2, V2, E2, ZL. So these are the parameters we are taking for the approximate equivalent circuit of transformer referred to secondary. And coming to the phasor diagram, so the right side we have the phasor diagram. So here I am taking voltage as the reference vector. Okay, V2 as the reference vector, that is it is indicated with OA. So here I am taking the points, that is O, A, B, C, D, E, like that I am taking. So in this one I am taking the voltage line as the reference, that is OA. And next, so here V2 lags I2. V2 lags I2. Okay. And next we have E2. So this V2 line is leading E2. And next we have two drops. Why? Because in this circuit we have R02 and X02. So here we have the current, that is I2. So depending upon these, we have the drops, voltage drops, that is I2 R02 and I2 X02. So here I2 R02 is represented with AD line, AB line, that is I2 R02, and next we have BC, that is I2 X02. I2 X02. So here the phase difference between this I2 R02 is phi 2, and the phase difference between I2 X02 is 90 minus phi 2. So here AB is equal to, from this phasor diagram or vector diagram, I am taking AB is equal to I2 R02 cos phi 2 and BC is equal to I2 X02 cos of 90 minus phi 2. So from the vector diagram I am taking OC. So OC is equal to, so if you observe this one, so OC is equal to OA plus AB plus BC. Okay, OC is equal to OA plus AB plus BC. So that's why I am writing this one. So OC is equal to OA plus AB plus BC. So from the vector diagram, OC is equal to E2. So OC is equal to E2, this line. So this one is E2. Okay. So OC is equal to E2. And next OA, that is equal to V2 plus AB is I2 R0 to cos phi 2 plus BC is I2 X0 to cos of 90 minus phi 2. That's why I am writing here. Same thing. And next we will write E2 is equal to V2 plus I2 R0 to cos phi 2 plus. So here we have cos of 90 minus phi 2. So from the trigonometric functions, cos of 90 minus phi 2 will write as sin phi 2. So that is E2 is equal to V2 plus I2 R0 to cos phi 2 plus I2 X0 to sin phi 2. So from this one we will rewrite this equation as E2 minus V2, that is equal to, that means V2 taking to the left side, that is E2 minus V2, that is equal to I2 R0 to cos phi 2 plus I2 X0 to sin phi 2. So secondary voltage, that is V2 is equal to E2 minus I2 R0 to cos phi 2 plus I2 X0 to sin phi 2. This is the secondary voltage. And finally, we have to write the percentage of voltage regulation. You know already the formula, that is equal to E2 minus V2 by V2, that into 100, that is equal to E2 means we have I2 R0 to cos phi 2 plus or minus I2 X0 to sin phi 2, that is V2 by V2, that into 100. Okay, E2 minus V2 by V2 into 100 means I2 R0 to cos phi 2 plus or minus. So why I am taking plus or minus? If it is a lagging power factor, we have plus value. If it is a leading power factor, we have negative value. That's why I am taking plus or minus. So I2 R0 to cos phi 2 plus or minus I2 X0 to sin phi 2 by V2 into 100. So here I am taking positive sign for lagging or inductive load and negative sign for capacitor or leading power factor. So here for lagging or inductive load, the voltage regulation is positive, and for leading or capacitive load, the voltage regulation is negative. So this is the expression for voltage regulation. And next, coming to the condition for maximum voltage regulation. So from the previous slide, we are taking the expression for voltage regulation, that is equal to I2 R0 to cos phi 2 plus or minus I2 X0 to sin phi 2 divided by V2. So that is to get the condition for maximum voltage regulation. So to get the condition for maximum voltage regulation, differentiate the above equation, that is voltage regulation equation, with respect to phi 2 and equate it to 0. That is d by d phi 2 of voltage regulation, that is I2 R0 to cos phi 2 plus or minus. So here I am taking plus, that is for the lagging load. So I2 R0 to cos phi 2 plus I2 X0 to sin phi 2 by V2. So that is equal to 0. Differentiate this one with respect to I2. So we have 1 by V2 d by d phi 2 of I2 R0 to cos phi 2 plus I2 X0 to sin phi 2, that is equal to 0. And after differentiating this one, we have I2 R0. So differentiation of cos phi 2 with respect to phi 2 is minus sin phi 2. So that is minus I2 R0 to sin phi 2 plus, so differentiating sin phi 2, we will get cos phi 2, that is I2 X0 to cos phi 2. So actually I did a mistake. So that is not I2 X0 to sin phi 2. Before differentiating, there is I2 X0 to sin phi 2, but after differentiating with respect to phi 2, we have I2 X0 to cos phi 2, so that is equal to 0. And next, I2 R0 to sin phi 2, so that is equal to I2 X0 to sin phi 2. And after simplifying this one, we have R0 to sin phi 2, that is equal to X0 to sin phi 2, so cos phi 2. So after simplifying this one, we have tan phi 2, that is equal to X02 by R02, so that is equal to phi 2 is equal to tan inverse of X02 by R02. So that is the voltage regulation of transformer is maximum when the load angle phi 2 is equal to tan inverse of X02 by R02. So this is the condition for maximum voltage regulation. And next we are moving to condition for zero voltage regulation. So actually we have seen that for lagging power factor and unity power factor condition, V2 is less than E2 and we get positive regulation. I already said this point in the expression for voltage regulation for transformer. So, but as load becomes capacitive, so up to now it is of the lagging and unity, and but as load becomes capacitive, V2 starts increasing. That is, V2 is greater than E2. Okay, V2 starts increasing as load increases. So at a certain leading power factor, we get E2 is equal to V2, and the regulation becomes zero. So at certain leading power factor, we get E2 is equal to V2, and the regulation becomes zero. So if the load is increased further, E2 becomes less than V2 and we get negative regulation. Okay, if the load is increased further, that is E2 becomes less than V2, that is for the leading power factor, and we get negative regulation. So for zero voltage regulation, E2 is equal to V2 and E2 minus V2, we will rewrite this equation as E2 minus V2, that is equal to 0. Okay, and next, so I am taking the regulation, the zero voltage regulation of transformer may obtain for leading or capacitive loads. That is, voltage regulation is equal to, so I2 R0 to cos phi 2 minus I2 X0 to sin phi 2 by V2. Why I am taking minus is, here I am considering leading power factor or capacitive load. That's why I am taking minus. So voltage regulation is equal to I2 R0 to cos phi 2 minus I2 X0 to sin phi 2 by V2, that is equal to 0. And so denominator, if we cross multiply with 0, the denominator is equal to 0. That's why I am taking only numerator, that is I2 R0 to cos phi 2 minus I2 X0 to sin phi 2, that is equal to 0. From this one, I am writing I2 R0 to cos phi 2, that is equal to I2 X0 to sin phi 2. After simplifying this one, we have R0 to cos phi 2, that is equal to X0 to sin phi 2. So from this one, I am writing tan phi 2 is equal to R02 by X02. So that is equal to phi 2 is equal to tan inverse of R02 by X02. So this is the leading power factor at which voltage regulation becomes zero while supplying the load. Okay. So for the maximum voltage regulation condition, we have tan inverse phi 2 is equal to tan inverse of X02 by R02, and for zero voltage regulation, we have phi 2 is equal to tan inverse of R02 by X02. Okay, this is the condition for zero voltage regulation. So next small topic is there before going to the testing of transformers, that is why transformer rating in kVA. So in interviews also they will ask for the code side why transformer rating in kVA in place of kilowatts. Why we are not taking kilowatt rating? That means we have to give explanation. So the copper losses of a transformer depend on current and iron losses and voltage. So you know already this one. The copper losses of a transformer depends on current. Why? Because the copper loss is I square R. Those are I square R losses. That is, the copper loss of transformer depends on current and iron losses on voltage. So iron loss depend upon voltage and copper loss depend upon current. So hence the total losses of the transformer depends on volt ampere, that is VA, but not on the phase angle between the voltage and current. But not on the phase angle between voltage and current. That is, the total losses of a transformer are independent of load power factor. That's why the rating of transformer is in kVA, but not in kilowatts. So in external exams also, they will ask for 2 marks this question. Okay. So next, coming to the testing of transformers. This is the very important concept. Okay. So the transformers can be tested by the following tests. Those are, we have totally 3 tests. Actually 4 tests we have, but in our syllabus we have 3 tests. So first is open circuit test. So this test is also called no load test. And second one is short circuit test. This one is also called as impedance test. And third one, that is Sumpner's test. Okay. And we have another one, that is load test. But in our syllabus they didn't give this one. That one, that's why I am taking, I did not take that one. Okay. So by using the open circuit and short circuit test, we can find circuit constant, that is R0, X0, R01, X01, R02 and X02. And secondly, we have to find out the core loss and full load copper loss. And lastly, we have to determine, that is predetermine the efficiency and voltage regulation. So these short circuit and open circuit tests are convenient to perform and very economical, because they provide the required information without actually loading the transformer. So firstly, I will take the open circuit test or no load test. So the open circuit test is useful to find no load loss or core loss. Okay, no load loss or core loss. And second one, no load current, that is I naught. So which is helpful in finding out R naught and X naught. So previously I said that, so the open circuit test and short circuit test, by using these tests we have to find the circuit constants, that is R naught, X naught, R01, X01, R0 to X02. Okay, so that's why, so in this one I am taking this one, so no load current I naught, which is helpful in finding out R naught and X naught. Okay, and next I am showing the circuit diagram or diagrammatic representation for testing of the transformer, that too under open circuit test. So this is the circuit diagram we are taking for this one. So in this one I am taking both primary and secondary windings with magnetic core, and in this one we have voltmeter, wattmeter, and ammeter, and no load current, that is I naught, and LV side and HV side, and V1. So in the open circuit test, the primary winding is connected to the supply voltage, that is V1, and the secondary voltage is in open condition. So at that time we have E2 is equal to V2. Okay, in this one we have the I2, that is the secondary winding current. Okay, so here wattmeter, voltmeter, and ammeter. So in the wattmeter we have 4 terminals. One is main, that is M, another one is L, that is line, and C is common, and V for voltage. So these are the 4 terminals we have for the wattmeter. This is indicated with W naught. So by using voltmeter, we have to determine the voltage reading, that is V1, and by using ammeter we have to calculate the I naught, and by using wattmeter we have to calculate the W naught. So coming to the explanation, that is the operation of the open circuit test on a transformer, that is one winding of transformer, that is usually high voltage winding, is left open, and the other winding is connected to supply of normal voltage and frequency. So previously I said that one winding of the transformer, that is usually high voltage winding, is left open, that is secondary winding, and the other winding is connected to supply of normal voltage and frequency. So the applied voltage V1 is measured by a voltmeter. Okay, the no load current, that is I naught. So in the diagram you observe that one I naught. So the applied voltage V1 is measured by a voltmeter. The no load current, that is I naught, by an ammeter, and no load input power W naught by a wattmeter. So why I am always telling the no load is, the open circuit test is also called as no load test. That's why I am frequently using that word no load. Okay, so the applied voltage V1 is measured by a voltmeter, the no load current I naught by an ammeter, and no load input power, that is W naught, by a wattmeter. That is as shown in the diagram. So as the normal rated voltage is applied, so in the actually in the practicals we are using the normal rated voltage, that is 240 or 220 or 230 volts. So at that time we have to take the normal iron loss will occur in the transformer core. Normal iron loss will occur in the transformer core. So hence wattmeter, that is W naught, will read the iron losses and small copper losses in the primary. Okay. So next, so as the no load current I naught is small, that is usually 1 to 3% of rated current. So actually rated current is 8.9 amperes in this one. So as the no load current I naught is small, then copper loss is negligible. So why? Because the copper loss is mainly dependent upon the current. So here the no load current I naught is small, then copper loss is negligible in primary and nil in secondary winding, So hence the wattmeter reading gives the iron losses in the transformer, and it is same at all loads. Okay, wattmeter reading gives the iron losses in the transformer, and it is same at all loads. So here iron loss is nothing but the P suffix I, that is equal to. So we are calculating the iron losses in this test by using the wattmeter reading, that is W naught, and next no load current, that is I naught. It is measured by using the ammeter, and applied voltage. So that is the voltmeter reading. It is taken from the V1, and we have no load input power, that is W naught is equal to V1 I naught cos phi naught. That is input power. That is on the primary side. That is V1 I naught cos phi naught. So here no load power factor, that is cos phi naught is equal to W naught by V1 into I naught. From the input power we are taking this no load power factor, that is cos phi naught is equal to W naught by V1 into I naught, and phi naught is equal to cos inverse of W naught by V1 into I naught. Okay, so next, no load backfill component, that is IW is equal to no load backfill component, that is IW is equal to I naught cos phi naught, that is equal to W naught by V1. So that is W naught by V1, and no load magnetizing component, that is I mu is equal to I naught sin phi naught. So that is equal to root of I naught square minus AW square, and no load resistance, that is R naught is equal to V1 by IW. So that is equal to V1 square by W naught. Okay, the next no load reactance, that is X naught is equal to V1 by I mu. So that is equal to V1 by root of I naught square minus IW square. And next, thus open circuit test gives no load loss, that is PI, that is the no load iron losses, and IW, that is the no load backfill component, and I mu, that is no load magnetizing component, and R naught, that is no load resistance, and X naught, that is no load reactance. Okay, this is the explanation for the open circuit test. Okay, and next coming to the short circuit test, this is also called as impedance test. So the short circuit test is useful to find firstly full load copper loss, and secondly equivalent resistance and reactance referred to meter inside. Okay, and coming to the circuit diagram, so this is the circuit arrangement for the short circuit test. So in the previous open circuit test, the LV side is that is LV side is in open condition, sorry, HV side is in open condition, but in this one the secondary side is short circuited with a thin wire. Okay, so same circuit arrangement, only difference is here I am short circuiting the secondary winding. So in the previous case we are open, but in this one we are short circuiting. So same here we are taking voltmeter to calculate the primary voltage or short circuit voltage, and we are taking ammeter. In this one we have to calculate the primary winding resistance current, that is I1, and we are taking wattmeter to calculate the losses, that is WS, and in this one also we have four terminals, the M, L, C, V. So M means main, L means line, C means common, V means voltage, and we have primary voltage, that is V1, and it is a AC supply, that means we have phase and neutral connections. Okay, so coming to the explanation of the diagram, so in this test the secondary winding is short circuited. I already said this one in the previous slide. So in this test the secondary winding is short circuited by a thick conductor, and a variable low voltage is applied to the primary winding. A variable low voltage is applied to the primary winding. So this is shown in the diagram, and the input voltage is gradually raised. So in this one the input voltage is gradually raised with the help of variac. Okay, so till up to we are varying the input voltage, that means up to we get the short circuited current. Okay, flows in the primary winding, that is I1, and next there is no output from the transformer under short circuit condition. So there is no output under short circuit conditions for the transformer. So therefore input power is all loss. So input power is all loss, and this loss is almost entirely copper loss. Almost entirely copper loss. So since applied voltage is very low, flux linking with the core is very small, and therefore iron losses are so small that these can be neglected, and so the reading of the wattmeter gives the total copper loss at full load. Okay, total copper loss at full load, right? Because applied voltage is very low, means flux linking with the core is very small, so iron losses are small. Then we will neglect those losses, and the reading of the wattmeter gives the total copper loss at full load. Okay, next coming to the calculations. So here full load copper loss, that is P sub U is equal to, that is given by the wattmeter we are using in the circuit, that is WS. And next we are taking applied voltage, that is voltmeter reading, it is V sub C, and full load primary current, that is ammeter reading, that is equal to I1, and coming to the full load copper loss, that is PCU is equal to I1 square R1 plus I1 square R21, so that is equal to I1 to R01. Why? Because we are taking the full load primary current, that is the primary side, that's why PCU is equal to, that is the copper loss is equal to, full load copper loss is equal to I1 square R1 plus I1 square R21, so that is equal to I1 square R01. I1 square R01, this is the full load copper loss, and from this one R01 is equal to copper loss or full load copper loss by I1 square. So where R01 is the total resistance of second transformer referred to primary. So R01 is the total resistance of transformer referred to primary. Okay. So, and total impedance referred to primary is Z01, that is equal to VSC by I1. Okay, total impedance referred to primary is from the circuit Z01 is equal to VSC by I1, and total leakage reactance referred to primary is X01, that is equal to root of Z01 square minus R01 square. So short circuit power factor, that is cos phi S is equal to copper loss by VSC into I1, that is the short circuit power factor cos phi S P sub Cu by VSC into I1, and thus short circuit test gives full load copper loss, that is PCU, R01, X01, and cos phi S. Okay. So this is the explanation for the short circuit test, and coming to the last test, that is Sumpner's test. This is also called back-to-back test. So although up to now we discussed about the two open circuit and short circuit, so although open circuit and short circuit tests are used to find out the efficiency and voltage regulation of the transformer accurately, so yet for determination of temperature rise, it becomes necessary to put the transformer on full load for several hours. So that means we have to apply the load in this test. Okay, so this test requires two similar transformers. Okay, this test requires two similar transformers. So these two transformers are fully loaded, and the power taken from the supply is necessary for supplying the iron and copper losses of both transformers. Okay, so I will show the circuit diagram for the Sumpner test. So this is the diagram we are taking for the Sumpner test. So in this one, I am taking voltmeter and single phase AC supply, and wattmeter W1 and ammeter A1, and we are taking three transformers actually. In those, where two transformers are similar rating, and third one is for the regulating transformer. So in this one we are taking voltmeter V2 and wattmeter W2. Okay, so it is namely taken as two similar transformers, that is M1, M2, and regulating transformer, that is R. Okay, and we have to find out the I1, I2, and V2, like that, and we have to use the switch. So coming to the explanation of this diagram, so the circuit consists of two similar transformers, those are main transformers, that is, and one regulating transformer, two main transformers, and one regulating transformer. The two transformers, that is similar transformers, is represented with M1, M2. These are connected in parallel across the same AC supply. These are connected parallel across this one, M1, M2 is connected parallel across the same AC supply with switch S open. So this one, here we are using switch. By using switch open, we are taking these two transformers, and with the switch S open, the wattmeter W1, so this one, the wattmeter W1, so this one, the wattmeter, when the switch is S open, the wattmeter W1 reads only core loss of the two transformers. W1 gives the core loss of the two transformers because the transformers are under no load at that time. Why? Because the switch S is open, and the secondaries are so connected that their potentials are in opposite to each other. Okay, the secondaries are so connected that their potentials are in opposition to each other. So this would be so if Vp0 is equal to Vnm. So in this one, Vp0 is equal to Vnm. So here we have. So Mn terminals we have Mn, Ut, and R2, OP, like that we are taking the terminals. So in this one, this would be so if Vp0 that is equal to Vnm, and P is joined to N and O is joined to M. So Pn OM. So here P is joined to O. So this one, the M2 transformer, the second transformer, P is joined to O, and next O is joined to M. So O is joined to M. So P is joined to N and O is joined to M. So in this condition, there will be no secondary current flowing around the loop formed by the two secondaries. Okay, in this condition, there would be no secondary current flowing around the loop formed by the two secondaries. And next, so here I am taking the regulating transformer. So that is R is the regulating transformer which can be adjusted to give a variable voltage and hence current in the secondary loop circuit. Okay, R is the regulating transformer which can be adjusted to give a variable voltage and hence current in the secondary loop circuit. So by proper variation of R, that is the regulating transformer, the full load secondary current can be made to flow. The full load secondary current can be made to flow. So in this diagram, the secondary current I2 flows from M to N and then P to O. So M to N and P to O. So M to N and P to O, like that from the secondaries. Okay. So and flow of primary current, that is I1, is confined to RQC BTU VR. So those are the terminals we are using, RQC BTU VR. That is this one. So RQC BTU VR. Okay. So like that the primary current is flowing, that is I1. Okay, and it does not pass through wattmeter W1. So the current I1 current is not passed through wattmeter W1. So hence wattmeter W2 reads full load copper loss. W2 gives the wattmeter W2 gives the full load copper loss, and wattmeter W1 continues to read the core loss of two transformers. So W1 wattmeter gives the core loss of the transformer, and W2 gives the copper loss of the transformer. So obviously the power taken is twice the losses of a single transformer. Okay, obviously the power taken is twice the losses of a single transformer. So that's it for today. So in this class we discussed about the voltage regulation of a transformer and testing of the transformer. In that one we use 3 tests: open circuit test, short circuit test, and Sumpner's test. Okay, and in the next class I am going to discuss the parallel operation of the transformer. Okay, thank you for watching this video.